Hello, so I've got an example here that will allow us to review how the vector equation of a line works, as well as the scalar equation of a plane and what sort of information we can get from that scalar equation. So in this example, it asks us to find a vector equation for a line that's normal to the plane x minus y plus 2z equals 3, and also this line passes through the point 4, 5, 6. All right, before we start, let's just get a sense of geometrically what's going on here. So we've got some sort of plane, okay, with scalar equation x minus y plus 2z is equal to 3. And we'd like to find the vector equation for a line that passes through this plane. But that line is orthogonal to that plane, right? It's perpendicular or normal. There's all sorts of words we can use to capture this idea. Okay, so if I looked at, the angle between the line and the plane, it would be 90 degrees. That's what normal means. This line also passes through the point 4, 5, 6. So how do we solve this problem? So there's two sort of components that we need to look at here. First, we're going to need to figure out a vector equation for the line. So what is that going to look like? So just as an aside, remember, if we've got some line passing through three-dimensional space, we can describe all points on that line by basically adding up components of a vector that's like parallel to that line, right? We call it sort of like a directional vector d, and a vector that connects us to the line. Okay, so we'd call that, let's zoom in here for a second, we'd call this vector b. Okay, and so if we wanted to reach, say, this point over here on the line, okay, if we want to get over here, right, well, this is going to be equal to b plus some constant times the directional vector, right? That vector is parallel to d, so that's some scalar multiple of d. Right, and we can get to any point on this line by basically traversing along the vector b and then adding some scalar multiple of d. A negative scalar multiple will take us backwards in the other direction, but we can reach anywhere on there. Right, so if we talk about the set of all points on that line being represented by a bunch of vectors x, then the vector equation for that line is going to be of this form. All right, scalar multiples of d plus this displacement vector that takes us to the line. And we usually say that if we want this whole infinite line, we say t belongs to the real numbers. So that's the vector equation of a line. So basically all we need to find to solve this problem is the direction vector, d, something that gives us the direction of the line, as well as a single point on that line, right? So that we can define a vector that takes us onto the line. Okay. So going back to the problem at hand, we can see that we basically already have b given to us in the problem, right? If this plane is sitting out in space somewhere, well, we know that this point 4, 5, 6 here, right, that's on the line. So if we take a vector and connect it from the origin to that point, that will be b. Okay, so we can say let b equal 4, 5, 6, and we've got that ingredient then. Now we just need the direction. So how can we get the direction of this line? Well, we've got to discern that somehow from what we're told about the plane that it passes through, right? We have an equation for this plane. Now, how do we get an equation for a vector that's normal to this plane, right? Because that's what's going to give us the direction. If we could find an equation for a vector that's normal to that plane, then we've got the directional vector for that line. Okay. So how do we get that normal vector? Well, remember the scalar equation for a plane. So again, let's go back over here. The scalar equation for a plane has the form n dot x is equal to b dot n. Okay. Where x is just represents the x, y, and z coordinates. So if I expand this equation, right, it looks like a bunch of vectors in here, but we call this the scalar equation because when you take dot products, you're just left with scalars. So if we expand this, we'll get, you know, if the normal vector has x component, let's call it nx, you'll get something that looks like nx times x plus the y component times y plus the z component times z. And that's going to be equal to b dot n. And b, the components of b and the components of n are both constants, so this is just going to give you some constant quantity. We'll call that d. Now look, this is basically just, right, if I call that a, b, and c, then I've got this equivalent expression. ax plus by plus cz is equal to d. Right? That's the more familiar way of writing out the equation of a plane, and that's what we've done up here. And sort of comparing these then, we see that a here is equal to 1, b here is equal to minus 1, and c here is equal to 2. Okay? And those coefficients then, going back to this, looking at the scalar equation, must correspond to directions of the normal vector. So this is just, you know, this is nx, this is ny, and this is nz. So we can just stare at the scalar equation and read off the coefficients to get the normal vector. So the normal vector is 1, minus 1, and 2. We didn't really need to do any work there, right? We just got the 1, the minus 1, okay, and the 2. Now realizing all that, we're done. We can just say, at this point, we've got the direction vector, d, we've got the displacement vector, b, so the vector equation for our line is equal to t times the direction vector, which is the normal vector of the plane, 1, minus 1, 2, plus the displacement vector b, 4, 5, 6. Okay. And there's infinitely many points on here because t is defined over all real numbers. So that's it. So that's the vector equation for the line. All right, hope that made sense. Thanks.